Hello my friends, welcome again to my video channel. Today we'll start a new project, a stereo amplifier, the A100-X from Musical Fidelity. It's an integrated amplifier, okay. It is a Class A amplifier. First surprise. Question mark in my eyes, what is a Class A amplifier in such a context? Don't understand it really, so let's have a look at it. A friend of mine brought this amplifier to me. It is not working, he said, and he made a short description. It is dead, obviously no output, irrespective of the setting with a phono, CD, tuner and so on. No output, okay. And he told me that this receiver was getting very hot when it was working, but this seems to be not a fault, this seems to be the result of the design of this amplifier. Class A amplifier, whatever it means, Class A always means high bias current. Maybe this is a problem. We will see later. The knob here is broken. It's plastic pin which is broken. It's for this on-off switch. Plastic is very reliable. It will break at any time. It's only a question when it breaks. And when the chassis gets hot, it will break earlier. We can feed it in, so we can switch on off. Okay. Here we have the same switch for the tape monitor. Volume. This knob was also a little bit loose. I only flipped it on the axis. I think the pot is loose. Anyhow, this is the selector, and on the rear side we have a lot of inputs and outputs, CD, tuner, auxiliary and so on. Here's a switch for MC and MM. I think it's for the magnetic and for the crystal tone system of the phono input. Here we have tape, monitor and record, and this is speaker output. The power consumption is 200 watt. I have to look for the schematic, but I think that the A100 means 100 watt. I assume totally on both channels together. The manufacturers usually do, they add the output and then say it's a 100 watt amplifier. Sounds better than 50 watt per channel. Well, first I will plug it on. I will increase the voltage with my variac and see what happens. Well, the input is dead. The reason is fuse is blown. That's not nice. This indicates a short in the power supply, power transformer, rectifier, first electrolytic cap. So I will not energize it any longer. I will open the case and look whether we can see it. Such a heavy blown fuse on the primary side here. It's a 3.5 amp fuse, slow blow. That's for 220 volt, yes. I think it's for 110 also. 3.5, There is no difference in the fuse between 220 and 110 volt. Suspicious. Anyhow, I will open the case. But I've just seen that the fuse here is a 2 amp fuse. Slow blow 2 amp. This would make sense. When we have 3.5 amps at 110 volt, we should have a 2 amp fuse at 220 volt. Could make sense, yes. I will replace it to get the option to measure the DC resistance on the inputs on the power cord. First I removed the Allen screws on the top. Then I assume that the chassis can be taken out, but it's not possible. Then I saw that this top cover is split into 2 parts. Okay, should be possible to take it out, but here we have, okay, I can take it out in this direction when I take out these screws completely. Here's a screw missing. The board should be squeezed down like this. but here we have no such a starter or distance holder, and someone has forgotten a screw. Well, not so critical, I think. These are the power transistors, and I see the top cover is part of the heatsink. That's the reason why it's getting so hot. Now we'll try to get it out, and I think there are screws also for this part here on the bottom side. It's a little bit tricky to open it. I took off all screws. There was a nut on the bottom side, and now I can take it off. Here we see the thermal grease. Okay, this is the power part. Oops. Same procedure. Well, now we have a look into the amplifier. Like this is strange. Okay, this is a Torii transformer. That's okay. Here we have 4 electrolytic caps. Maybe one of these caps has a problem, or all. This is the final transistors. Hey, what is this? What the heck is this? Have you ever seen such a design? Surprise, surprise. This is a collector of the transistor. It is wired directly. Here is one, here is one. And the other 2 transistors are wired in the same way. This and this. It's a piece of wire. Oh. And obviously someone has resoldered it and soldered in a new one, because this one is unsoldered. There was a, yes, there were 3 times blank wires, and the 4th one is an enameled wire. It's not original, and the color of the shape of the solder shows me that it was, or it's getting hot when it works, when the fuse isn't blown. This pot is also loose. There's a piece of wire in it. Is it a clamp or what is it? Ah, it's a ground. Looks like a ground connection. Yes, it's a ground connection. This should be squeezed in. It's loose. Oh. Here we have the bad switch. On off. I'm just preparing to take out this board. It's rather loose. Okay, the screw is missing. Bolt can be removed, but here the board is not fixed. Also on this side, you see this board is very flexible. On this board, this bolt here fixes it to the chassis. Here's another screw. Why am I doing this? Well, I've seen that we have obviously a problem with the electrolytic caps. You can see it. They look bulged. This is maybe the reason for the problem. This power switch is off. So we have here the primary winding alone. And I can measure here a DC resistance of approximately, what does it say? 11 ohm. Yes, it is 11 ohm DC resistance from here to here. That's okay for the DC resistance. That's an indication that we don't have an interruption. And I think also not a short, so the problem is not the power transformer. So now we have contact between the two pins as it should, and when I switch it off, then we have no contact. Nothing. Well, this indicates that this switch here is okay. This switch is okay, fuse is okay, primary side of the transformer is okay. Now we can focus on the secondary side and on the electrolytics. I could flip out the board. 3 additional screws for the hinge connectors. Be careful with these switches. There's another switch on the rear side for magnetic or crystal system for the phono. Well, and we can see here now the electrolytics. They are bulged. 8709, September 87. I take them out and measure them, but I'm sure they are bad. With the pot with the ground connection. And dust, dust, dust like a desert. So the first thing I have to do is use a vacuum cleaner and take out all this dust. There are 2 fans, and that's the reason why this amplifier is so full with dust. There is no filter. It is directly fed from the air, from the outside air into the amplifier. This is not a good design. But before we continue with our work, we should have a look into some details, the schematic of this amplifier. The descriptions in the net are a little bit interesting. Let me say interesting. It's not a standard configuration in the output. We see here it's a push-pull configuration, plus and minus 35 volt. But the emitter is connected here to the supply rails. It's not an emitter follower. It's a common emitter circuit. And these 2 halves are driven. Of course, one is for each half. But we have seen on the front panel it is described as a Class A amplifier. This is not a Class A amplifier, but there's a very high bias current flowing. I've read in another articles, I will give you the link in the description of the video, that the bias current is set to 700 milliamps. 700 milliamps with a voltage of 70 volts, so we have a power consumption of 50 watt without output signal. This is one channel, the other channel also 50 watt, that's 100 watt. Another author describes it with 150 watt. There are obviously different versions on the market, and one author says he had about 100 units on his workbench and he never found 2 identical units. Okay, I can't check it, don't have so much units, but obviously we have here a thermal problem. Such a high bias current flowing through these transistors cause of course a lot of heat, and that's what also my friend described. This amplifier gets brutal hot on the surface. 60-70 degrees Celsius. There's a temperature which is too hot for your finger. I've read a proposal to reduce this current, to reduce the heat. I will do it. But in general, we see we have here such a configuration. Here we have the input differential amplifier for each half of the signal. It's also another common design. Another author wrote it would be possible to replace one of the transistors simply by a constant current source, and then we would have a Class A amplifier, and it would also work because each half is fully equipped as amplifier with differential input and control of the output current. So this one, for example, would operate when we would here use only a constant current source. It is strange, and it's interesting to read some articles and the descriptions in detail how it works. Again, the link is in the description of the video, or the links. And here I have a description from another website. It's in German language, but this is this amplifier, and the guy described nearly everything what he did. He replaced, of course, his capacitors, which are blown. These are obviously not blown or bulged, but they have to be replaced, cleaning, and there are some brown spots here. There is a Zener diode which is getting hot. This area here, it's getting hot. We see it, traces over the decade of use. These are new electrolytics. Okay, I will start with the power supply, take out the electrolytics, measure them, check out the rectifier here, whether it is still okay. Maybe the rectifier is also damaged. We shouldn't forget the primary fuse was blown, so maybe also the rectifier is bad. And he replaced also some pots, switches, and so on. It's a question how much the repair is going, whether we leave the path of a simple repair and go to a restoration. The project here is a little bit limited, and I don't want to do everything which is described here. Maybe it's necessary or advisable, but I have some limits here and in my project, so I do what is necessary to get it running, but I don't improve it. There are also proposals to remove the preamplifier in one of the projects. Is it this one here? Yes. Someone described it. It's a different type, not this one. Here we have this amplifier we have, and he did also some modifications and replacements. Okay, I will see what is necessary, and also will talk to the owner what to do, but he wants only a working amplifier again, because he was satisfied with it in the past. So I think when I repair all faulty components, it will be okay for him. The 4 caps are out. They've been installed here. The first one, they all should have 22 millifarad. The first one has 12 millifarad, and the dissipation factor is 0.7. It's the tangent delta of the loss factor. It should be nearly to 0. And when I go to quality measurement, it's 1.4. Cannot be accepted at 120 Hz. When I go to 1 kilohertz, we have a dissipation factor of 4. That's it. Again, tangent delta. We have nearly a resistive component here, and the quality drops down to 0.2. I will do a voltage measurement and isolation measurement also, because this factor does not cause a blown fuse. It only causes a lot of hum, bad quality in the signal and so, but not a blown fuse. And this one has also 12, same result. Or are they also bad? Could be. Again, 12 millifarad. These 4 caps are not so nice. Do a voltage check also. Same result. They all have the same result. That's a little bit surprising, because when they are bad, but they are definitely bulged. Oops. Sounds like a switch. Is this part of the design? Can't imagine. Comes out. I will apply a voltage. They are specified up to 35 volt DC. 35 volt DC. This is a supply voltage of the amplifier. This is the first capacitor connected to my power supply. It only runs up to 30 volt. You see always when I increase the voltage we have a small charging current, that's okay. .30 volt and a little bit more. No indication that we have a short circuit. I have to discharge it carefully. And number 4. So the result is these caps have no short. By the way, these two resistors which were in series to these caps were not burned, they were not overheated. There's no sign of any overheating. R47.47 ohms, they are obviously okay. Not overheated, nothing. I will check the resistance. We're measuring .6.7. Okay, that's okay. The cable has some resistance and the other one has .7. Yes, they are both okay, not overloaded. Maybe indeed that we have no problem with the caps and these resistors. Why is the fuse blown? Do we have a problem with the rectifier? But first I will check this. I will throw them away anyway. But now I'm a little bit curious what happened. I opened all 4 electrolytics, they're all okay. It's only the plastic which was bulged. Maybe the heat or aging, whatever it is. The can is okay. Could have been that some gas is okay. This could be that some gas is squeezing up and bulging it because this is more or less tight. So I will open one of them totally. Nothing. The can is okay outside. The pressure relief here is also okay. Nothing happened. Only the dissipation factor. The quality is very, very bad. Well, we have a very high capacity. 22 millifarad is high, but that it is so bad I didn't expect. Anyhow, this is a scratch from the knife when I opened it. They have to go, they are too old. I will replace them by new ones, and now I will focus onto the rectifier. Now we will check the AC chain from the power transformer up to the rectifier, and then nothing because the electrolytic caps out and the coupling resistors between the two capacitors for the positive and negative side are disconnected, so we have indeed only the rectifier in operation. And the DC voltage is plus and minus, and AC they end up here. There are no further connections. I also unsoldered the fans. They're not rotating. The only connection here we have is the AC connector to the terminal switch, but this is obviously okay as we have seen. This is a bulb, and on the rear side we have here the connections of the speakers. The set is not connected in the moment. I switch it on with a screwdriver. Where is a screwdriver? Just to switch it on. Dum, dum, dum. It is on now. Plug it in and then I increase the input voltage. Watch the current and see what happens. I'm at 100 volts. Now I'm measuring the AC voltage over the rectifier, just to get an imagination. 26 volt. What did I expect? 40 volt. Yes, it depends upon the output voltage. We have a full bridge rectifier. On the board it is stated with plus minus 24 volt output of this rectifiers. So that's 48 volt. For 48 volt we would need 35 volt or so. Let's increase to 220 volt. Nothing happens. No flames, no smoke. It is 57, 58 volt AC. I made a second measurement with 230 volt AC input. I lost the video, forgotten to switch on the microphone. It was late in the evening or early in the morning. 58 volt secondary. With this configuration we would have a DC voltage of plus 39, ground minus 39, totally 78 volt. I measured it, it's correct. I added here 2 small electrolytics and the output 100 microfarad just to have a measurement. It's unloaded. So I have the peak voltage, no ripple. This means we have an unloaded voltage of 39 volt DC. Okay, when it is loaded it goes down, and the second voltage behind the series resistors, between these two resistors we have seen, are a little bit smaller. There's a voltage drop, but on the board there is stated with 24 volt DC. Don't believe, I think it's 35 or so. I have to be careful when selecting the new electrolytic caps. 35 volt is a little bit, I need more than 40 volt. I have to look for the right electrolytic caps, not to have a new problem. Now we are at the end of part 1, and I have some time to order new electrolytics. Then we will repair the power supply and see whether the fuse blows again. Maybe it was simply the high inrush current and the fuse aged over the years, could be. We will see in part 2. Stay healthy, stay tuned. See you on this channel.